Hello folks, this is Tom from anti-proton.com, and this is going to be, I'm going to try to make it quick, a quick set of answers to my 3 most common questions emailed to me, because I get dozens of questions, and if I haven't gotten back to you and you've emailed me, it's not because I don't like you, it's not because I've, done whatever, it's because I just forget and get just piles of stuff. And I mean, I get like 100 or 200, whatever it is, work emails a day too. So I have lots and lots of stuff. So if you have a question I haven't gotten back to you, ask me again. I'll probably remember this time. Anyway, the 3 most common ones, I'm going to put links on the side of the screen so that you can click the link and go right to the question you want just in case, because I'm probably going to refer you to this video if you ask me these questions in the future. Not because I don't like you, it's just because I'm lazy. Anyway, uh, question number 1, can I test food for radioactive contamination, and if so, how, what, with, and why, etc., etc. Basically, how do I figure out if this unnamed, unmarked can of food contains radioactive contamination? Question number 2, what is a safe level of radiation? I get that one constantly. What's a safe level in counts per minute, microsieverts per hour? People ask me this question. You may not be happy with my answer, just to let you know, but I'll answer it anyway. And number 3, what kind of Geiger counter or detector should I get to detect Fukushima radiation, as people always call it for whatever reason? I'm going to get to these. Let me tell you, just to start as usual, I'll say my typical disclaimer. I am not a nuclear professional. I am not a doctor. I have no such qualifications whatsoever. I am an enthusiast, an amateur, and somebody who's really interested in the subject and knows probably a hell of a lot about it, because I've spent a really long time learning about this kind of stuff. But I don't hold any of those qualifications, so keep that in mind. I am an amateur. That means this is just my opinion of what's true, I guess you could say. But then again, what is true? Anyway, let's start out with testing your food for contamination. It's kind of hot in here right now. There are 2 types of contamination that you're going to find in your food when it comes to nuclear radiation. I'll define those as gross contamination, like massive contamination, large-scale contamination. That would be like fallout from a nuclear event landing upon the food. Okay, it's not a little bit of radiation, it's a lot of radiation, right? You dust it off the box. There's that type. Then there's the very, very, very small, insidious type called trace contamination. I will call it trace contamination. Oops, drop that. And that's when this thing has X number of becquerels per kilogram, some little tiny small amount of radiation. And by the way, when I say small, I don't want you to perceive that I'm trying to say that it's somehow less dangerous. I am not equating the lesser amount of it, the traceness of it, as being not dangerous or anything like that. So don't get that idea, because I get that a lot from people. When I say it's trace or minuscule or hard to detect, I don't mean safe, it's not there. I just mean trace, small, hard to detect. You know what I mean? So, looking at the first one, you live in a small town near a nuclear power station, 10 miles. The nuclear power station has an event. There's a gas rupture, nuclear gas gets blown out into the air. Maybe not a meltdown, but still it's enough. And it rains all over the place. And, kind of a little 3 mile island-ish. Of course, 3 Mile Island actually was a partial meltdown, but you get the point. Something like that happens. It's not Fukushima, or in fact, it could be Fukushima. For example, if you live in a small town, Fukushima happens nearby. You just happen to be in Fukushima. A train going by derails and a nuclear material breaks open and goes all over the place. Things like that happen. Something where radiation is released in a large amount. I do not mean the smaller trace amounts. I'm talking like a big amount. And you see people wandering around the streets with the suits on, testing stuff. I mean, it's like that. Your place has been declared a national disaster area. The National Guard has come in and they're all in suits. I'm talking like that. In that scenario, you're not looking for trace radiation. You'd love to know if this has trace radiation that could one day cause you potential cancer, maybe. You'd like to know that. But at this moment, you're really hungry because the government hasn't brought in like food supplies yet, for everybody, and it's kind of not doing so well. Something's gone wrong. Some rogue nation has detonated a nuke or something. In that kind of scenario, what you're really looking for is if something is really radioactive, like actually has radioactive dust on it. You pick up a piece of fruit or vegetable off the ground, it could have trace radiation in it. You're not going to be able to detect that without a lab. But you want to know whether or not this thing is, the dust that you're wiping off of it is like, dust from the nuclear meltdown or a catastrophe. Stuff that, like, if you lick it, could actually literally right then and there make you sick. Forget cancer, right then get you sick. Okay? For that kind of scenario, a small handheld Geiger counter is perfectly acceptable. Absolutely, no problem. Take it, put it in a place, and you run it for about an hour, and you get a good background, which means you sum up all the counts you get in an hour, divide by the number of minutes you did it, and let's say my background count is about 38 counts per minute right this moment. We're pretty close to that, right? Put it by the food source, do the same exact test in every conceivable way, and then subtract the original background from the new test, and you get the difference, which could be, let's say, 50 or 60 counts per minute, telling you it's probably contaminated. Okay? That's fine. What people really usually are asking is they're asking for trace contamination. For trace contamination, meaning 100 becquerels per kilogram, 50 becquerels per liter, small amounts, that kind of stuff, that's usually taken care of by state and governmental testing facilities. I know nobody wants to hear that, but it's true. And the reason is that you need significantly complex machinery and equipment to determine that. I mean, I have some of it myself, but it's expensive and very complicated to use. To give you an idea, I'm probably going to spend longer on this question than the other two, so just, if I'm droning on a little, just keep that in mind. For starters, let's answer the question of why is the Geiger counter not the best thing for detecting that, okay? The reason is this. Let's take an example, because people work better with examples. Let's say that this can is contaminated. Let's say we know it's contaminated, okay? We know that this can, and it's not contaminated. But let's say it's kitty food, actually. Let's say this can has 100 becquerels per kilogram. That means if I had a kilogram of these cans, it would be going through about 100 decays per second of cesium-137. See? Cesium-137, like this little guy right there. Why isn't it focusing? Focus, focus, focus. Focus. There you go, cesium-137. Okay, so we know that, right? Now this is not a 1 kilogram can. This is I'm looking over here at my math answers that I wrote up. This is a smaller can. It's like 85 grams. So we're looking at 8.5 decays per second of cesium-137 in this can for a long time. Now, that equals out, I'll just give you the answers to this. You can use a calculator if you want to follow along. But that equals 15,300 decays per hour from this can. For cesium-137, you have beta and you have gammas coming out of it, right? We're just going to look at cesium-137. There's so many other isotopes out there. We're just going to look at cesium-137. That's the one everybody's all freaking out about. But anyway, the other ones, trust me, strontium-90 is worse than that as far as I'm concerned, although that's my layman opinion, but I believe it's either equal or worse because strontium-90 is a bone seeker. Oh my god. But just looking at cesium-137 for a second. The betas coming out of this, they're being emitted tremendous numbers of betas. In fact, where was it? I just looked it up. 15,300 of them every single hour. But the problem is that the betas can barely make it through the aluminum on the side here. Most of those betas are less than 500 kiloelectron volts. And there's some higher ones, but most of them are way less than that. Most of them aren't going to make it out of this. And I'll show you what I mean. Here, let's take this Geiger counter, right? And we're going to show ourselves a little demonstration. We're going to take the cap off, and we're going to put, that just is not working right. I need a third hand. And we're going to put this near it. Actually, let's pull it back about an inch, because we want to account for the can. Alright? 24,000 counts per, it's a huge number of counts per minute, alright? I'm not going to get too specific about it. Now let's put the can in between. This is not a scientific test. I'm just kind of giving you an idea. Now all we're picking up is gamma, right? Because all the betas are being blocked for the most part. Not the most scientific test on Earth. But you see that there's several orders of magnitude difference. Oops. The reason is because the betas are blocked by the aluminum. They're also blocked by the kitty food itself as they're being emitted. So ones that are right on the very edge might make it through, but ones that are on the other side of the can are probably not going to make it through. So you almost have to discount the betas. It's not that they can't be detected, it's that they will not be reasonably detected. So let's look at photons only. 85.1% of beta decays that come out of this are going to result in a photon, a gamma ray. We're not going to look at the 32 keV ones, the low energy ones, just in case anybody out there knows about those and asks, because the aluminum in the can will block most of those too. Uh, so just looking at the higher energy ones, we can expect that for 15,300 decays per hour, 13,020. We'll round that up. We'll just round everything up. So 13,021 photons per hour will be emitted from this can. Sounds like a lot, right? Sounds like we should be able to detect this. Okay, when you take this and you put it up against the Geiger tube, and you can actually use something called 4 pi r geometry to figure this all out and everything, but let's just rough ball it right here. All right, this would be 50% of it, right? 50%. We're not quite getting 50 because a little bit of it coming this way can kind of spill over the sides. So I'd say we're getting about 40%. Wouldn't you agree, about 40%? By the way, the estimates I'm about to give you don't really matter. Even if you capture the whole thing, it's not very much. So 40% we'll say of the can is being detected, okay? 40% of 13,021 is 5,208.4 photons per can per hour. Now, we divide that by 60 minutes, we come up with 86.81 photons per minute. Well, that shouldn't be bad, right? This thing the Geiger counter is only getting 38 counts per minute. That's over double the counts per minute on that. It should be easy to detect, right? Well, here's the problem. The actual ability of the tube over there to detect gamma rays, according to the manufacturer, is less than 1%. Now, we're going to say 1%, which is actually a best case scenario, taking into account a few other things. In other words, I'm jacking it up to make it more sensitive. It's actually less sensitive than what I'm doing. I'm giving it the benefit of the doubt. Given it the benefit of the doubt, I come up to 0.01 times 86.81, which is equal to 0. That's less than 1. 0.8681 counts per minute. Less than 8.81 counts per minute. Now my Geiger counter runs for 1 hour in the office here, and in that 1 hour period of time I get a mean of 39.533333 counts per minute. My plus or minus on that population for a 1 hour test is 1.5404 blah 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 blah. What I'm trying to get to you is that even if this was cat food rated at 100 becquerels per kilogram, the change in my graph, if I graphed out the data with my Geiger counter, would be below my confidence level. It would be below my error. It would be below everything. It would be below any possible statistical significance. Which is not to say it can't be detected. It's being detected. There's no way. Even if only if I only had 1 becquerel per year, if it hits that detector, it might be detected. It's not that it can't be detected. It's that it cannot be detected in a means that you can easily detect and figure out, statistically. Now, if you jack this up to 400 or 500 becquerels per kilogram, that changes things. At that point, it might start falling into being detectable. But that's what I'm trying to say. Now, the biggest problem is this. Even if you were able to detect it with something more sensitive like the scintillator, way more sensitive, the scintillator might be able to detect it down to that level. Here's the problem. The scintillator can tell you, if it's connected to a gamma spectrometer, what's actually causing that. Is it cesium-137? Or is it just maybe reasonably harmless potassium? Or radium-226 because it's a plant growing in the ground? The Geiger counter can't tell you that. So Brazil nuts, bananas, potatoes, tomatoes, most of your fruits and vegetables, beans, all that stuff is going to detect positive if you're able to detect it at all. And you're not going to have any idea if that's what's causing it or not. So you might sit there starving to death in your little underground shelter because you think everything's radioactive and you have no idea what actually is causing it. And then if it's something like strontium-90, which is a really nasty bone seeker, my God, keep that away from yourself. I have a sample right over there. Strontium-90, most of its beta particles aren't even going to make it through the metal housing again. So that's the problem. You can detect large-scale contamination with the Geiger counter, but it is not a good idea to use it for low-level contamination. And using metal or lead to shield it's not very effective with the Geiger counter. Very effective with the scintillator. Not very effective with the Geiger counter. The reason is because they can detect such high-energy particles. They detect muons and weird stuff like that all the time. A lot of people don't realize that. They think it's detecting alpha, beta, gamma. A lot of what we're detecting is muon radiation. So that's the answer to number 1. I'll be really fast with the other 2. I just wanted to give you the reason why, because I get this question constantly from people. Yeah, you can buy a Geiger counter. I recommend owning a Geiger counter. But the equipment you need to buy is going to cost you a lot if you want to detect food contamination. A couple $1,000. Easy pie. And you need skill to use it too. Skill, like lots of skill. you can go, like, for example, to Polymaster. And I think I was talking to the guy at FLIR at a expo just yesterday. We were comparing. We whipped out the ruler and measured our Geiger counter, so to speak. We were competing with one another over who had the best portable gamma spectrometer. I won. But anyway, he was talking about how FLIR has a unit that does this too, but Polymaster sells the 1409 or 3. I'll put a link to it in the page. It's a food tester. You just put in the food and hit the button, and it's like push button simple, and you don't have to know anything whatsoever, and it'll tell you if it's dangerous or whatnot. That's all nice and everything, but those units, like that unit's almost $4,000, like $3,000 something dollars, very expensive. And you're going to really have to determine whether you think you need something like that in the United States. Now, I can't tell you whether or not you're at risk and need it, because it's not my place to tell you. I can tell you I wouldn't buy one. Oh my God, no, obviously not for this little tiny microscopic trace radiation that we have around here. But maybe you feel that you need that. But if you're going to do that, make sure you're not smoking or drinking or anything else that has a much higher chance of harming you. Like eating red meat, for example, which I love red meat. I don't have any problem doing that. But I mean, eating red meat, there's all these other things like walking across the street that are tremendously dangerous to do statistically, yet people don't care about those. They only care about the radiation, which can harm you too, but people don't necessarily always think about these things rationally. Now, number 2. I'm only on 2, but I'm going to be quick. If you did want to detect Fukushima radiation, what could you do it with? Well, Fukushima radiation isn't special. It's not different from other radiation. It's just like all other nuclear fissile disaster radiations. There's been like, 12 or something meltdowns in the world? I mean, I can actually list them if you want to. I mean, I can list a couple of the big ones right off the top of my head. Fukushima, that's 3 cores. Chernobyl, that's 1 core, I believe. Windscale, that's 1. It's not a core, but it was like a big box thing. But it was a reactor. It caught on fire. Oh my God. That was Windscale. 3 Mile Island, that was 1 core. Idaho, that was 1 core. That was 1 Idaho. I think we've had multiple Idahos, although nobody knows about them, even though they're not secret. You can look them up, but like nobody seems to know about them for some odd reason. All of those are emitting the same sort of stuff in various levels depending on the nature of the accident. Some produce more radioiodine, for example, than others, but the basic releases are similar. Not the same, similar. The biggest culprit out there is strontium-90 and cesium-137. Strontium-90 is over there. I didn't pick it up for this. You probably could detect it from Fukushima if you were if you're on the West Coast, but you wouldn't know you were detecting it. It would be so small it might add some tiny microscopic amount to your background reading if you were testing it, but realistically you'd have no way to know that without a spectrometer. Right after Fukushima, I bet it was probably detectable for a short time in some of the rain, but you wouldn't know you were detecting. Even if you had a positive detection, you wouldn't know it, because you don't know the difference between that and radon washout, which is what accounts for most of the radioactivity in the rain that we see. Radon washout, I don't know why people think that comes from Fukushima. I mean, it's weird, bizarre stories spread by the people that think that, like, aliens live on the TV and stuff like that. It's all that weird conspiracy stuff. Actual science knows that radon washout has existed for a long, long time, like, forever. And it, forever, since the Earth existed and has had rainfall and so on. Fukushima fallout was falling on the United States. It was confirmed by many universities of many different labs, and to this day it's still up there in the air, floating around here and there, little bits of it. And every time they have a big release over there, probably a little bit more comes out of it. But even as much of it as there is, you wouldn't know you were detecting it with the Geiger counter, even if you did. The 2 types of detectors out there that most people are going to buy would be either a pancake detector like this, which is good for contamination. For contamination testing, you test to see if something's contaminated with this. I use it for area monitoring too, but that's not its general purpose. It's usually for contamination. Like, for example, if I have a rock sample here also, I could use it to see whether or not the rock sample is radioactive. It's very sensitive, and that's what it's good for doing. It is great for doing that. What it is not necessarily good for is background monitoring, I don't believe. I don't think that it is, personally. It's not an energy compensated tube, and there's some issues involving that as well too. The other type you can get are types that have just a solid tube that is not exposed per se. Some of these guys, like here's an old CDV 700, some of these guys have a tube that has a window in the end that can sense and sniff alpha particles in the same way this does, but it's smaller and more secured, and some don't. They're typically sensitive to beta and gamma only, sometimes just gamma. Those type, like the little CRM100 detectors and stuff, those are great for area monitoring, for background area monitoring. They're very, very tough. They're very, very rugged, and for the money, I think they're definitely worth it. What I'd say to you is this: if you can afford, if you're going for a Geiger counter and you're not buying it for something silly, you're buying it for something you can actually use it for, testing rock samples, seeing what's radioactive in your environment, and everything like that. Um, I would say if you can afford a pancake, go for it. They're great. They're wonderful. They're super sensitive. If you can't afford a pancake, don't feel bad getting the other type because they're perfectly useful, and I own them too. Very, very useful. I love my regular tube probes just as much as I like my pancake. Although pancake is more useful, I believe. Now getting on to number three. And number three, the third question was, let's see, what is a safe level of radiation? Actually, I think that was supposed to be number two, but whatever. The answer is this. There is no such thing as a safe level of radiation, meaning there's no such thing as a dose of radiation that has absolutely zero harm. But then again, the word safe doesn't usually mean zero chance of risk. Safe usually means relatively risk-free. For example, eating food is not risk-free. You can die from illnesses from eating food poisoning and stuff, but most of the time that we eat food for the majority of our life, we're not going to get terribly ill. It will happen, but not often. And so that's why when we go by the store and we see some food and we want to stop over there and get some fries or something, we don't usually worry about it because we know that it's generally safe, which is a very relative term with gray lines all over the place. I know people that won't eat fast food and hide in their house and they don't want to come out because they're scared of everything. And they have a different opinion of safe than I do. I know people that will walk right into a room full of high radiation field and be like, who cares? I know people that smoke and drink all day and they know their risk of cancer is high from it, and they think it's not really something to worry about, so they have a different opinion of safe. Safe is a very relative thing. To a degree, you can statistically determine some kind of empirical level of what you would call safe. That being the case, background radiation that we're exposed to all of the time, I would say would probably be, and I'm not a professional, and disclaim it one more time, I would say is probably reasonably safe in so much as it is a risk that is not elevated above the normal because it is the normal. Whatever your normal risk is all day long without anything changed or added to it, you're just standing there out in the middle of the woods by yourself, risk is pretty much your normal risk. And things above it would be maybe less safe depending on your interpretation of safe. Background radiation will cause cancers in people. You can't say it will always do it, and you don't know if people have had it, but you know that it probabilistically should be generating some cancers, but it's still considered safe. 22,500 people per year die from cancer from radon, natural radon in the ground. I mean, how safe is that? So it depends on what you consider safe. Most of the radiation the majority of us will be exposed to in our lifetime is not going to cause tremendous negative effects. That's backed up by CDC and FDA data, and there you go. So I'd say the majority of us are reasonably safe. Some of us not, depending. If you're out in the middle of the West somewhere and you're near a water supply that was used for uranium mining and has uranium tailings in it, you may be unknowingly drinking or breathing in air and water and so on that could be reasonably highly contaminated, and you may not be safe. Now, what people really want from me is they want a magic number. If my Geiger counter says more than X number of counts per minute, I need to go run for the hills. That is an incredibly hard answer to give you. I like to say that a smart idea would be to figure out what your long-term background is for your area. Let's say your Geiger counter typically is always at 50 counts per minute. If you're in Denver, it could be 80. If you're, in the eastern United States, it could be down in the 20s. Because it depends, and different Geiger counters have different background ratings. I mean, my background for my Ludlum here, the scintillator, can be as high as 2,000 counts per minute. So figure out what your background level is for an extended period of time, a couple hours, sample it over a couple days, get an average, and then look to see if that increases or decreases by several times. An increase by several times will show you that something is probably wrong or in your environment. I don't know if that would immediately be a cause for alarm, or if that would be unsafe. What I would say you want to be more careful about is if you pull your Geiger counter out and you hold it on something and you start hearing thousands of counts per minute. That means that you probably have something to be concerned about. I don't know how unsafe it would be, is so freaking relative. All these various factors come into play, the energies, the isotopes, and everything. But to give you an idea, um, when I take something radioactive and hold it up, I'm not going to die like right here in front of you doing this. My 102,000 counts per minute. Now, my cancer risk from holding this little guy, it might go up a little bit, probably statistically speaking by some amount. Um, but then again, I see people smoke cigarettes and then try to talk about radiation safety. You got to keep all of that in mind. All that stuff's relative. There's so many things out there that can harm you. You don't want to focus on just one of them, but you don't want to forget any of them either. So that's why I'm a fan of background monitoring your environment, and citizen monitoring too. So I guess I've kind of evaded the hell out of that question by not giving you a straight answer, and that is because there is no straight answer. How's that for an answer? There is no straight answer. It's kind of like saying, how many cigarettes can I smoke and it be safe? What's a safe level of cigarettes to smoke? It's kind of a hard answer, a hard question to give. You could say that if you only smoke 2 per day or 3 per day, your chance might be this or this. If you smoke 2 packs, it might be this. But there's no real way to answer that question, nor is there a way to really answer your question. So I hate to be wishy-washy and flim-flam, but not only am I not qualified to answer it, but even if I were, I don't think there really is an answer. It's not necessarily right to say that there is no safe level per se, because background isn't really going to increase your risk above what is normally background. So it is self intrinsically, well, it's counterproductive. It's automatically that way. It's automatically reasonably safe if you consider your own background itself to be safe. So wishy-washy. God, I should be a politician if I keep answering like that. This has been Tom from anti-proton.com. God, I hope this helps everybody a little bit better than it seems for me. Maybe, I don't know. But ask away and I'll refer you back to it. Bye-bye.